Hi! In this video, we explore a very important topic, the relationship between the increasing or decreasing behavior of a function and the sign of its derivative. Observing the graph of a smooth function, that is a function with a tangent at every point, we may notice that the tangent behaves like the function. In the sense, when the function is decreasing, as you can see here, also the tangent is decreasing. And when the function becomes increasing, so does the tangent. Now, a straight line is increasing or decreasing depending on whether its slope is positive or negative. For the case of a tangent line, the slope is the derivative of the function at point, so we may guess that the function increases or decreases depending on the derivative of f is positive or negative. This is almost true, but we have to add some condition here. The important condition is that the domain where this happens must be an interval. So we can prove that if the function f is differentiable on an interval I, the function is increasing on I if and only if the derivative of f is positive on I, in large sense, and decreasing on I if and only if the derivative of f is negative, in large sense, on I. Now, why must the domain be an interval? Isn't enough to have f prime greater or equal than 0 to guarantee that f is increasing? And moreover, can we say that something like f increases strictly if and only if f prime is strictly positive holds true? Well, let's respond to these two questions through two examples. For the first question, we take this example. F of x equals minus 1 over x, which is well-defined function for x different from 0. We can easily plot its graph, it's an hyperbola. And we can easily see that this is differentiable for every x in the domain. The derivative is 1 over x squared, so clearly strictly positive. But this function is not increasing, as the graph suggests. For example, you can check that f of minus 1 is larger than f of 1. For the second question, let's consider this example. Take the function x cubed, which we know to be a strictly increasing function because of the properties of powers. But when you compute the derivative and you wonder if this is always strictly positive, that's false because at 0 the derivative is equal to 0. The relationship between the sign of the derivative and the monotonicity of the function offers a simple criterion for determining whether a point is an extremum. Here we present this in the case of maximum. So let f be a function of variable x defined on an interval I of the real line, x star a point of the interval I, and be the function such that f prime of x is positive at left of x star, negative at right. So we may imagine that the function is increasing at left, decreasing at right. And moreover, at point x star, we just demand that the function is continuous. If the function is differentiable, of course, it is more than to be continuous, so it is also continuous, and the theorem remains true. But this means that it is not needed that the function be differentiable at point x star. And this will have some impact, as we will see. Then, under these conditions, the point x star is a maximum point for f on I. So this means in particular that if I is the domain of the function, this point is a global maximum. Now let's see why this is true. We take the interval I and we divide in two parts. The part of points at left of x star, we call this A, and the part made by points at right of point x star, we call it B. The two are two intervals, as you see, and we have that the derivative of f is positive on A, which is an interval, and therefore the function will be increasing on A. So we may imagine that the function here increases in this way, so it goes up. And then if it grows, we may say that if we pick a point here, the value of the function will be smaller than the limit when x goes to x star of the values of the function, which is the left limit for f when x goes to x star. And because of the continuity, this is the limit. So it is in particular the value of the function at point x star. A similar argument, so here we have the limit value is the value of the function. A similar argument holds at right. Derivative is negative, the function is decreasing. So it means that if we move from the right to left, the function is like if it is increasing. And so in particular, the values of the function for x at right or b are smaller than the limit value of f when x goes to x star, this times to the right. So the right limit for x going to x star plus of f. But again, the function is continuous, so this limit coincides with the full limit for x going to x star of the function, and this is equal to f of x star. So in conclusion, we see that on A, so at left of x star, f of x is smaller than fx star. At right of x star, f of x is smaller than fx star. Therefore, f of x is less or equal than fx star for every x. And this means that x star is a maximum. So why we do not require the differentiability of the function at point x star, but just the continuity? The simplest possible is the following. Take the function f of x equal minus absolute value of x, which has clearly a maximum at 0, but it is not differentiable at 0. And here you can see that the derivative of this is 1 at the left of 0. It is minus 1 at right, so positive derivative at left, negative derivative at right. The function is continuous at point, and therefore the assumptions of previous theorem are verified. So we can apply the theorem to this case, but we could not do that if we would require the differentiability of the function at maximum point. For minimum, an analogous statement holds, and I invite you to formalize this statement and to prove it by adapting the reasoning we have seen here. Now, to conclude this video, let's see how to apply these ideas on a simple example. Determine the minimum maximum points for this function f of x equal x times e minus x when x is in the half line 0 to plus infinity. So here what we do, we calculate the derivative of f. The function is clearly differentiable, and we get the derivative of the product. It is 1 times e to minus x plus x times the derivative of e to minus x, which is e to minus x times the derivative of the exponent minus 1. So factorizing e to minus x, we have this times 1 minus x. Now this derivative is positive if and only if this factor is clearly positive. 1 minus x is positive. So if and only if 1 minus x is positive, that is if and only if x is less or equal than 1. It is convenient to summarize this information in a table where we mark the domain, so from 0 to plus infinity, and the significant point, 1, where the sign of derivative changes. So we have that sign of derivative is positive here and negative here. And therefore, about f, we can say that on the interval from 0 to 1, derivative is positive, function is increasing. On the interval from 1 to plus infinity, derivative is negative, function is decreasing. Moreover, at point 1, the function is well defined, and it is even differentiable, so it is continuous. And therefore, this means that x equal 1 is a global maximum for f, because you see it is a maximum for the full interval, 0 to plus infinity. Now, what about the problem of determining the minimums? Now, here we could say that a unique candidate could be this point, 0. And in fact, the function is increasing from 0 to 1, so definitely 0 is a minimum point for the function on the subinterval 0, 1. So we could say it is a local minimum for the moment. We cannot be sure that it is a global minimum because the function starts decreasing after 1, so we don't know if it falls below the value that it takes at 0. However, here we can solve this problem by looking at the function. The function at 0 is equal to 0, while at every other x, we can see that the function is in any case positive, because x here is from 0 to plus infinity. So combining these two, you see that this local becomes a global because the function is always above the level it takes at 0. So this finishes the solution of the exercise.